Hi, hello, welcome to Jadov Civil Academy. In this class, I am going to discuss about solutions for previous Ecet questions in TS Ecet examination 2020 in the subject strength of materials. Right? Let us start our discussion with the first question. The first question which is asked is the relation between three elastic moduli, that is E modulus of elasticity, G modulus of rigidity, and K bulk modulus. Say here we have three elastic constants E, G, and K. The relation exists between these three is option B, that is E equal to 9 kg by 3K plus G, the direct relation, direct formula. So now we'll discuss one more question. A cylindrical wire is stretched by tensile force such that the volume of wire is constant. Find the Poisson's ratio of a material of wire. Say this is a, a cylindrical wire, right, and which is stretched by applying tensile force like this. Because of application of this tensile force, the volume is constant. So its volume is not changing. So we can write volume is constant. Okay. So when the volume is constant, I can write that the volumetric strain, that is change in volume by original volume of that cylindrical object is equal to 0. Is equal to what? 0. So whenever the volumetric strain of that object is 0, then its Poisson's ratio mu is equal to maximum. Mu is equal to maximum, right? And most of the engineering materials are incompressible materials. The Poisson's ratio value varies from 0 to 0.5. 0 is the minimum value, 0.5 is the maximum value. So here the volumetric strain is 0, then the Poisson ratio is maximum. So the maximum value of Poisson ratio is 0.5. So option D is the correct solution for this question. So let us see one more question here. From bending shear force and bending moment topic. A prismatic beam ABC is simply supported at points A and B, spaced 8 meters apart, and has an overhang of 2 meters. A uniformly distributed load of 15 kilonewton per meter is acting over a entire length AC, and the concentrated load of 50 kilonewton is acting at C. The bending moment at support B is. So based on this question, I have drawn a loading diagram here. There are three points A, B and C. Over this A, B, C, there is a UDL acting over the entire beam. The UDL is acting, that the magnitude of UDL is 15 kilonewton per meter. 15 kilonewton per meter, and this beam is simply supported at 2 points, that is point A and point B, and they are 8 meters apart. The distance between two support is 8 meters, and this overhanging portion length is 2 meters. At the end of the overhang at the point C, that is at the point C, there is a concentrated load of magnitude is 50 kilonewtons. So, from this problem, he asks us to calculate what is the bending moment at the support B. So, to calculate the bending moment at support B, you have to take a section over the B. You know, the definition of bending moment is what? It is the algebraic sum of the moments of forces which are acting either left of the section or right of the section. So this is a section. You can take the algebraic sum of the moment of all the forces. You can take either left of the section or right of the section. So for this case, I will take right of the section. Right? All hogging moments are positive for me. I am taking sign convention. Hogging moments are positive for me, and sagging moments are negative. So let us write the bending moment equation with respect to support B. It is MB is equal to 50 is the point load, and it is at a perpendicular distance between the point B and the 50 kilonewtons is 2. So I can write 50 into 2 and it will give me the a hogging bending moment. So it is positive. Then I have a UDL of 15 kilonewton per meter acting over a between the points B and C, that is 2 meters. So 15 into 2, that will give you the conversion of a UDL into point load, where that point load is acting now at the middle of this 2 meters. So it will be 2 by 2, 2 by 2. Again it will give me the hogging moment, so it is plus. So the 50 into 2 100 and this 15 into this 2 get cancelled, 15 into 2 30. So 100 plus 30 is 130 kilonewton into meter is the bending moment about point or about the support B. So option C is correct for this question. So let us discuss one more question here. It is on a theory of simple bending. A beam is subjected to sagging bending moment, has a cross section which is unsymmetrical I section, having overall depth is 300 mm. The bending stress at the top and bottom are respectively 100 mm and 50 mm, 50 MPa respectively. The position of neutral axis from the bottom of the section is, so I have a I section here. It is unsymmetrical I section. So like this, right? If I draw the bending stress for this is the neutral axis. The bending stress would be like this. The bending stress distribution is like this. And this is the compressive bending stress. At top we have a 100 MPa, 100 MPa, and at the bottom we have a 50 MPa. And he asks us to calculate the position of neutral axis from the bottom. So I am assuming that from the top the position of neutral axis is x and overall depth of the beam is given, that is 300 mm, right? It is 300 mm. Okay. Now it is assumed as x, then what would be this depth? It is how much? 300 minus x. The depth of neutral axis tension zone is 300 minus x. Clear? Now simple to calculate the depth of neutral axis from the bottom. We have a two triangles, the triangle 1 and triangle 2. Just apply a principle of similar triangles, we will get. So from the first triangle I can write 100 by x, that equal to 50 by, from the second triangle, 50 by 300 minus x, 300 minus x. Now if you simplify these, we will get 100 into this 300, 300 minus x and 50 into x. So 50 into x is equal 300 into 100, that is 30,000, 30,000 minus 100 into x, that is 100x. Okay, 100x. This is x. Now if you take this term here, x terms here, we will get 150x is equal to 30,000. Right, 30,000 like this. Now from this I will get x is equal to how much? 200. If you simplify this, we will get x equal to 200. But see here, the question was asked that calculate the depth of neutral axis or position of neutral axis from the bottom, from here to here. From the bottom, how much it is? 300 minus x. 300 minus x. So just substitute here 300 minus, what is x value? X value is 200. X value is 200. So we will get from the bottom of the beam, the depth of neutral axis is 100 mm. 100 mm. So the option C is correct for this question. So let us solve one more problem here. So it is simple problem again. The rectangular beam of 10 centimeter width subjected to a maximum shear force of 60 kilonewtons and the corresponding maximum shear stress is 3 megapascal. What is the depth of section? So that we can calculate. We know that when the rectangular beam, the maximum shear stress tau max is equal to 1.5 times tau average. The maximum shear stress induced in the rectangular cross section beam is 1.5 times tau average. This is a fundamental formula. Right. What is the tau average here? We can write this tau max is given is 3 megapascal and 1.5 times, that is tau average is shear force given by area of cross section, that is B into D. So in this equation we know F value, B value, we don't know what is the D, that we need to calculate. So from this I can write D is equal to what, 1.5, right, into F. What is the F value? It is 60 kilonewtons, that I convert into newtons only. So if you multiply it with respect to 10 cube, we can convert kilonewton into newton, right? So 15 to this, and by this 3 will get in this direction. 3 into, what is the B value given? B is 10 centimeters, so we will convert it to the mm. So it is 100 mm. 10 centimeter equal to 100 mm. Now this 1.5s are, this is 2s are, right? These 2 ones are 2 30s are, right? And here we have a 2 zeros and here 3 zeros, 1 zero cancel. Finally we get a 300 mm. So our options are in what? In centimeters. So 300 mm equal to how many centimeters? That is D is equal to 30 centimeters. D equal to how much? 30 centimeters. So option B is the correct for this question. So we'll discuss one more question. The sudden change in shear stress distribution diagram at across the section shows. Right. To answer this question, we have how to calculate the shear stress across the cross section at any depth, that is given by tau equal to F into A into y bar by IB. This is a fundamental equation which is easy to calculate the shear stress at any depth of the beam, right? So this is IB. Now here F is the shear force and A into y bar is the first moment area of the section, I is the moment of inertia of a section about central axis, B is the width of the section. So if you see the relation between tau, the shear stress tau and B, it is inversely proportional. Tau is inversely proportional to 1 by B, which means that if your shear stress is suddenly increases, your width is suddenly decreases. It is increases and your width is decreases. So if you see the option, the sudden change in CSS distribution diagram across the cross section shows the sudden change in the width of the section. Sudden change in the width of the section. So for example, if all of you know that for I section, if I take I section, if I take here, this is the I section. So for our understanding purpose, I am drawing this, right? And it is a neutral axis. If you draw the shear stress at top is 0 and up to this bottom of the flange, it will be like this. And as long from the width actual B to it is reduced the width of the web. So this width is like this, it is reduced to up to this. So as long the width is reduced, your shear stress distribution is increases like this. And similarly with bottom, and then it will be like this. So the shear stress distribution for your I section is like this, right? See here, up to here it is okay, parabolic. Of sudden changing in width of the beam, there is a sudden increase in the shear stress, right? So there is a inversely proportional relation we have between shear stress and width of the beam, right? So we have a question from torsion. The diameter of a circular shaft increased by increased by 40 mm to 80 mm. All other conditions are remains unchanged. Then how many times the torque carrying capacity is increased? So this, to answer this question, you should know what is the pure torque equation. That is T by J is equal to Z theta by L, right? G theta by L, and here one more term is tau S by R. You know the terminology. T, it is the torque required. J is the polar moment of inertia. Z is the rigidity modulus. Theta is the angle of twist. L is the length of shaft. And tau S is the shear stress induced in the shaft. R is the radius of the shaft. So let us take any two conditions. So let us take these two conditions. So I can write from these two conditions, T is equal, right, J into G theta by L. G theta by L. So what they are given in the problem, all other conditions are remain same, except initially we are initially the diameter of the shaft is 40 mm. Then what will be the torque carrying capacity, and if it is increases to 80 mm, what will be the torque carrying capacity? So let us discuss this. So for first we need to calculate what is the J. How to calculate J? So tau equal to, it is pi d square by 32. For solid circle, the polar moment of inertia is pi d square by 32. And these conditions remain same, that is g theta by L. Right. Now substitute initially, what is that? T equal to 40, diameter of shaft is equal to 40, pi into d square. D 40 square is how much? It is 1600 square. 1600, 40 square into 1600 by, it is 32. When it is, when the torque at 40 mm dia and remaining conditions are unchanged, that is g theta by L. G theta by L. So now calculate the torque carrying capacity at diameter 80, right? Then it would be pi by 32, same, pi by 32. What is the diameter now? It is 80. 80 into 80, 6400. 80, 80 how much? 6400. And remaining all other conditions are same, that is g theta by L. G theta by L. So this equation I can write 4 times pi by 32 into 1600, and other remaining conditions are g theta by L. So the, if you see the options here, the how many times the torque carrying capacity is increased. So if you say for 8 for what tau equal to 40 mm, it is pi by 1600 by 32 into g theta by L. For it is 84 times the tau 40. So the option B is correct answer for this question. Right. Then in power transmission of a shaft, if the polar moment of inertia of a shaft is doubled, keeping the length same, the torque required to produce the same angle of twist is. So to answer this question, first you should know what is the angle of twist, how to calculate angle of twist. So theta equal to TL by GJ. GJ. So from this I can write G J theta is equal T into L. So what are the terms? G is the rigidity modulus, J is the polar moment of inertia, theta is the angle of twist, and T is the torque required to produce, L is the length of the shaft. So what he asked us to calculate? Torque required to produce the same angle of twist is. So write down torque T here. From this I can write T equal to G J theta by L. So in this, for a material G, rigidity modulus is constant and angle of twist is same and length is unchanged. So what is given? He has doubled the polar moment of inertia of the shaft. So I can write T is equal to G into 2J, double means 2J into theta by L. So I can write when double the polar moment of inertia, then there is a increasing in torque double the original value, that is 2 times G J theta by L, right? It is 2 times the original value. So option C is correct for this question. So then we have a small question here. From the given M by EI diagram, calculate the maximum slope at A. So this diagram given in the problem. So how to calculate slope at any point? Say it is A is equal to area of M by EI diagram. This is a fundamental rule. Area of M by EI diagram, right? Area of M by EI diagram. So area of M by diagram is this. It is, we will take it is symmetric. We can take this half portion of the triangle. So write down, calculate triangle. Area is half base. Base is 2 meters, right? And height is 60 by EI. This is the height, 60 by EI. Okay, 60 by EI. So then these two get cancelled. The remaining term is 60 by EI is the slope at A. So option B is correct for this question. So then we have a direct question here. A simply supported beam of span L, uniform that is flexural rigidity, is subjected to concentrated load P at the center. The maximum deflection of beam is. So it is a simply supported beam and it is acting as a central point load here. The deflection, maximum deflection will be like this deflection curve. We will get the maximum deflection at the center point below the load. So this is Y max. For this case, Y max is equal to PL cube by 48 EI. So option C is the correct, PL cube by 48 EI. This is a direct question. So that's all for SM. It is a part 1. Part 2 will coming soon. Thank you.